This example I want to go through next is to find the Taylor expansion of one of those functions. I chose cosine of x because there's one for sine of x in your book, so if you want to look at that one, I'm going to do exactly the same example. But we're going to find the expansion of cosine of x not around a equals 0, but around a equals some other point. So I picked 2 pi over 3. Okay? But the procedure is the same. In the end, we'll get an expression for cosine of x equals this thing, but this thing will be different because we're doing our expansion around a different point. And the reason for doing it around a different point is because you're changing where your approximation is going to behave the best. So if you take a look at the video where we actually graph the approximations, you'll see the difference between the sine x around x equals 0, a equals 0, and sine x around, I think that was the a equals pi over 3 I did in that video. It's not the same series, but you're going to see a similar thing happen. If we graph this one, you see a similar behavior. Okay, so what we're going to do, though, we're still going to use the same procedure. We're going to find successive derivatives of cosine is negative sine. Derivative of, you know what? Let me write it like this, so it's a little bit easier to see. And of course, these are the same derivatives that I had on the board the previous time, right? Because I'm just taking derivatives of the same function. So that part doesn't change, right? And I'm going to do all 8. And so this would be cosine. Okay. But the second part is going to change because if I'm looking here, I need the nth derivative at the point A, which in my previous examples was 0. But here, I want to do A equals 2 pi over 3. So I have to evaluate all of these not at 0, but at 2 pi over 3. So cosine 2 pi over 3. So what is this? Go back. Okay, here's my unit circle. This is 2 pi over 3. This is going to be x coordinate is negative 1/2. Y coordinate is root 3 over 2. Okay? So cosine of 2 pi over 3 is negative 1/2. Okay. First derivative is going to be negative sine of 2 pi over 3. So I'm getting negative root 3 over 2. Second derivative is going to be negative cosine. So I'm going to get 1/2. Third derivative is going to be hard to fit them all on this board. So I'm going to stop here because after this they're going to repeat. Okay? Right? This is going to be cosine of 2 pi over 3, so this is negative 1/2, and then I'm going to put plus repeat. So, because I'm not around 0 or pi over 2, I'm no longer getting that my terms are equaling 0 for either the evens or the odds or whatever. I have root 3 over 2, and I got 1/2. So I'm going to end up with a much more complicated form for my final answer. Okay? So let's see what we have. C0, right, is f of 2 pi over 3, so that's just going to be this. C1 is going to be this guy over 1 factorial. C2 is going to be this guy over 2 factorial. So I'm just going to write it as times 1 over 2 factorial. And by the way, it's just a good plan when you're doing these not to work out the numbers because it looks all gross if you're going to try to make an nth term formula. The last thing you want is to be multiplying stuff out because you'll never see the pattern. And then C4 is going to be negative 1/2 times 1 over 4 factorial. Now, because they repeat, I can just go right back. C5 is going to be negative root 3 over 2 times 1 over 5 factorial, etc., etc. So it's minus 1/2, minus root 3 halves, 1/2, root 3 halves, and it goes like that. Okay, but I'm always remembering that I have to multiply by the 1 over n factorial as that guy's here. So now if I just want to write these guys out, I have to remember that my form is going to be like this. So what I have is going to be cosine of x, n equals 0 to infinity, cn x minus 2 pi over 3, which I just erased, but it was there. That's the a to the n. Okay? So let's write it down. C0 is negative 1/2, and then that's 0, so that's just 0. C1 is minus root 3 over 2 times x minus 2 pi over 3. C2 is 1/2 times 1 over 2 factorial x minus 2 pi over 3 squared. C3 is root 3 over 2, 1 over 3 factorial, x minus 2 pi over 3, then with the cube. Okay, so this is my n equals 3 term. My n equals 4 term, I'm back to the negative 1/2, right? And out of space. Now my 5 term and now I've got 6 non-zero terms. 1, 2, 3, 4, 5, 6. I can keep going because I see what the pattern is. It's negative 1/2, negative root 3. Now I'm positive 1/2 and positive root 3. So I'm going to write down 2 more just for kicks. Okay? We want to notice something about these. Right? We want to notice that I figured out these nth derivatives, but it's not all of it. You always have the factorial, and then you have the x minus a to the n, and then whatever. Okay, fine. So there's a bunch of them. Now, the question is this good enough? So, yes, no, depending on what the question is, right? For my purposes, I will not ask you to write down an nth term formula for this, unless it's extra credit, okay? Some people will require for the end of the problem that you figure out what this is in terms of an nth term formula. So let's go through and look at how you would do that for this particular example. Okay? That's a good example because you can kind of see where it comes from. So it is a little bit complicated, right? So that makes it a good example because we can like grapple with it. So the thing is, if all of these terms were the same, it would be easier to come up with the formula. The way it was with the sine x and the cosine x around x equals 0, right? We noticed, oh, it's just all the even terms or all the odd terms, so we can do 1 over 2n factorial or whatever. Here, you've got even terms and odd terms. The even terms actually have a 1/2. When we talk about even and odd, I'm specifically talking about the power here, which is our n, right? So the ones that are even, because they come from the cosine, have a 1/2, and the ones that are odd have a √3 over 2. That's why I didn't multiply it all out, because you can see those then in each of those terms. Each of these things has an x minus 2 pi over 3 something, but some of them have a coefficient of 1/2, and some of them have a coefficient of √3 over 2, and some things are positive and some things are negative. Okay, so it's a bit of a mess. But we can see, at least first thing, that the odd ones have the √3 over 2, and the even ones have the 1/2. So if I break this up into the even ones and the odd ones, okay, so two separate pieces. And my even ones, so for my even one, I'm going to do x minus 2 pi over 3 to the 2n, right? That's my even, 2n. Okay? I know I have a 1 over 2n factorial. I don't have a space. Crap. All right, let me see if I can fit this in here a little bit better. Make it a little smaller over here, so we have some space. Okay? I know I have, look, 1 over 2 factorial, 1 over 4 factorial, 1 over 6 factorial. I know I have a 1 over 2n factorial, and I'm always going to have something like that. Not always. I'm often going to have something like that, right? Because I'm always divided by n factorial when I do these guys. Okay? I know that each of these even ones have a 1/2. And then I know that they change in sign. So if I look at it, I've got negative 1/2, positive 1/2, negative 1/2, positive 1/2. So I have a minus 1, and I start from n equals 0, but I want to start with a negative because when I calculated it, the first term was negative. So I probably want to put like n plus 1 up here, right? Because when I put in n equals 0, then I should get a negative 1. And if you think about it, does this formula work? If I put in n equals 0, a minus 1/2, 1, and that whole thing is 1, right? Because anything to the 0 is 1. What about the n equal, the next one would be this guy. With n equal 1, I'm going to get a positive 1/2. I get 1 over 2 factorial, this guy to the 2. So that looks like this works. But this is for the even terms. This is just the even terms. I still have to do these odd terms too. Okay? But in the odd terms, I'm going to do the same way as I did the even terms. I'm going to leave a lot of space so I can write it. X minus 2 pi over 3. And I'm going to start with 2n plus 1 because I'm starting from n equals 0. I want my first term to be 1. I know I have to have the 1 over 2n plus 1 factorial. I know I have a √3 over 2. And I forgot to get mine. I need to do my -1, so I'm going to stick it up here because. And then my first one should be negative. So n equals 0 would give me +3 and +1 here as well. Okay. And then that's going to work for the even ones. Right? You don't always have to split these up into the even ones and the odd ones. If you do, for example, it's going to depend on both the function and the point. So if I did it a equals pi/4, I would just end up with a bunch of √2/2's everywhere. So I wouldn't have to do even and odd ones separately. But for some of them, you do have to do them separately. Okay, so it really depends on the form of the actual original function. Okay, so this is probably the more complicated example, which is why I wanted to go through it. But that's our nth term formula for cosine of x around a equals 2 pi/3 with times. All right.